Pass the homework mark. I have two worksheets here. You might have me totally Right, so on the desk there should be three blank things. There should be a four-sided two-page worksheet. Yes, thank you. And also your mark homework. If you don't get your mark homework, that could be because you haven't had it. And yeah, I know you were absent like for the past. So I'll give it back to like if you can come to the stuff and do the copy of the worksheet. The one that, oh, not this one. Like there should be another one that should be marked. Okay, but because you were absent, you did not have that end. Okay, so you can come to me after class. I will bring your copy. And yeah, we will be working on some of these questions later today. Okay, yeah. So after we finish this topic, after we read this topic first. But right now, I wanted to take out the worksheet from last lesson. So the worksheet with a lot of blanks, okay, and we stop at so this worksheet that says bonding and structure, okay. If you haven't brought this, you can jot down the notes on your notebook, okay. Right. So we will pick up from the covalent bonding part. Okay, so you can use the space below to jot down some notes, or if there isn't enough space, you can use your notebook. Okay? Right, so we are on this page right now. Covalent bond. If you don't have this worksheet, jot it down on your notebook. Okay? Thank you.
I'm not sure.
Okay. So if you haven't got right, if you haven't got your worksheet, you can come over here and collect your worksheet. Okay, so because there is one that doesn't have the name on it. Okay, and I think okay. Right. So let's start. Last time we looked at what covalent bond structures can be. Okay, so there are two subtypes. One is simple molecular substance. The other is giant covalent structure. Okay, so what's the difference between these two types of structures? So you may write it down on the side. With structure type number 1, so with type number 1, you will see strong covalent bonds. So write down, so with structure 1, simple molecular substances. What do you see in the structure? What do you call those orange forces? They are the strong covalent bonds, right? Do you see these rigid lines, okay, holding the atoms together? Those are strong covalent bonds, right? So strong covalent bond. Where do we find these bonds? We find these within a molecule. So this is what within means, inside one molecule. But then, what about between? So you know the difference between within and between. Okay, within a molecule, you see strong covalent bonds. What about between molecules? Do we see any forces holding the molecules together? Actually, there is. I just did not label it last time. So can you use dotted line? okay, to draw these interactions. Okay, these are called weak when the walls force. Okay, so right now put down these two things in here. You have strong covalent bonds between molecules. Within molecule, and you have weak when the walls force. So weak when the walls force between molecules. Okay, I'll label it here as well. So between molecules. So can you draw this on the side again? You have CO2. So this is what a CO2 molecule looks like. It has covalent bond from within a molecule. So this is within a CO2 molecule. What about between multiple CO2 molecules? So let's draw two CO2 molecules side by side. Between CO2 molecules, you have these weak forces. So between CO2 molecules, that's what between means. Not the difference between within and between. You need to see the difference. Okay, if not, you will answer the wrong thing in the exam. So there's weak when the walls force. This one. Okay? Right, so that's what simple molecular substances have. They have two types of interaction. One is strong, the other is weak. Okay? And the strength depends on where you find those forces. Okay? If you see one within a single molecule, that's the strong one, the strong covalent one. But when you look at between two molecules or more molecules, if there are more CO2 molecules, it will still be bound by these same weak forces. Okay, so that's the first thing to note. What about with giant covalent structure? Yeah, so you can finish studying this first. Very, 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 very important. This is clear, right? Yes. So now we have structure type number 2. Giant covalent structure. So giant covalent structures, they have mostly just strong covalent bonds. Okay, so strong covalent bonds within the giant molecule. So that's what giant covalent structure means. There are many, many atoms connected together. Take diamond as an example. So you see diamond. Diamond is made of carbon. Okay, so you have a lot of carbons linked tetrahedrally. Okay, so we used this term last time. Tetrahedrally means they form something that looks like a chicken leg. You know, this looks like a chicken leg. Okay, so they form this structure that resembles chicken leg. Okay, and then it expands outward like that. Okay, so you have a structure that looks like this. Okay, so this is what giant covalent structure means. There are many, many strong covalent bonds. And you don't see any when the mouse falls here for this example. Okay, but later I will show you one giant covalent structure which happens to have the weak when the mouse falls, just like simple molecular substance. Okay? Okay, so any question about what kind of interaction you can find in simple molecular substances and giant covalent structure first? Okay, that's how you tell apart these two structures. Okay, because then we will look at some simple molecular substance example below. Okay, remember this placeholder, we forgot to fill this in last time. Okay. Right, so below, can you name some compound examples of simple molecular substance? So if oxygen, hydrogen, and nitrogen, they are all elements. Do you remember what elements mean? What does the term element mean? How many types of atoms are there? Just one, yes. So write down element. How do I know these three are elements? Because they contain only one type of atom. So it contains only one type of atom. Compounds, okay, you learned this since form 3, okay, they contain more than one, yeah, or I like to say 2 or more, yeah, type of atoms chemically bonded. You must mention the word bonded, okay, chemically bonded in the answer. So more types of atoms chemically bonded. So any examples you can think of? What is the gas that we breathe out? CO2, yeah, so can you draw CO2 in here? What about the gas that cows emit in their fat that would cause global warming? Methane. So what's the formula? It's CH4. And then there is also water that is vital for life, okay, so H2O. These are all compounds. As you see, not just one, but two or more types of atoms chemically bonded. So can you draw them out for me? So you have CO2, C, yeah. Is there a question? No? Okay. So CH4, and then finally we have H2O. And after completing the worksheet from last lesson, you should know why sometimes we draw single bond, sometimes we draw double bond, okay? And now I'm going to refresh your memory. Do you remember that we draw these circles? Just look at the worksheet. You did one example on CO2. And you can now use that to explain why. Why do I draw two lines between the C and the O? Why not just one? That's because when carbon and oxygen are to form bonds, how many electrons should they share to help each other become stable? What do you see? How many? Okay, so let me draw it like this here. So can you fill in these symbols? So you have CO2, you have CH4, and then you have H2O. How do I know, or how do you know when to draw double bond, single bond, or triple bond? It's by looking at the group number. Okay, so remember that carbon has atomic number 6. What's the electron arrangement? 2, 4. Okay, so you can use dots to represent the electrons from carbon maybe. Okay, so you can draw 1, 2, 3, 4. And oxygen has atomic number 8, which means the electron arrangement is 2, 6. Okay, and we can use cross to represent the electron from oxygen, or maybe I'll just use circle. I'll use a different color circle here. Yeah, can you see that when they are to form bond, how many electrons has to be shared between each pair of C and O? 2 pairs. That means a double bond. Okay, so that's how you know it's a double bond. It's not random. It's not that you are drawing it randomly. It's by doing this exercise here, or finding out how many electrons these atoms should share in order to help each other gain stability. Okay, so that is not at all random, let me tell you. So can you put this back down? So CO double bond. A double bond, okay, so a double bond is made of 4 electrons, 4 shared electrons. In other words, 2 shared pairs. 2 pairs of electrons means 4 shared electrons in total. And then what about CH4? Why do we just show a single line between them? Because that's a single bond that contains only how many? 1 pair or 2 electrons. Very good. So can you also put down carbon, Z equals 6. So this is why what you learned from last, I don't know how many lessons ago, the atomic number, the electron arrangement. You need to apply it, okay? If not, you wouldn't know how many bonds to draw between those atoms. So for hydrogen, of course, it's very easy. It is the simplest element, so it has only 1 electron. So as such, we will just draw 1 electron contributed by hydrogen. Well, and let me remind you, in the exam, you are not allowed to use different colors like I'm doing now. So you should not use blue circle and red circle. You should instead use dot and cross instead. Okay, it's just that I want to make it more clear, okay, where the electrons come from. So finally, we have H2O. So H has atomic number 1, O has atomic number 8, which means, as usual, you will have dot, cross, or dot here in this case, and then you have how many red dots left on O? 4. There should be 4 left. Is that clear? Is that clear? Okay, how we get these bonds. Okay, so can you draw a simplified structural formula of these molecules? Okay, so when do you know you should be drawing these structures here? Okay, and when do you know you need to draw these structures? What's the meaning, what's the difference between these 2 types of structure? This type of structure, we call it electron dot cross diagram. is a hassle to draw. These structures on the side, we call them structural formula, as they only show you the bond between the atoms. Okay, so pay attention to the wording in the exam. When they ask you for electron dot cloud structure, they mean these in yellow. When they ask you for structural formula, they mean these. Okay, these are structural formula. Okay, and nevertheless, you can only draw the structural formula at this level from the electron dot cloud structure. So you can only get the yellow one first, and after that, you can get the green one. You cannot get the green one from scratch. Okay, is this clear?
Yes.
Oh.
Yes. Okay. So you can work out. Yeah. So it can be used to work out the structural formula. Okay. You have to find the electron dot cloud structure first. Okay. And that's simple molecular substance. Then we look at some giant covalent structures on the next page. Okay, even more intense. Okay, but any question so far? Yeah, I think I need to tap the screen from time to time to keep it open, okay, so it doesn't, shut down. So next up, on next page, I want you to put down another big title here. So in here, we just explore simple molecular structures or simple molecular substances. They are all simple because for CO2, when you draw two CO2 around each other, when you draw two CH4 around each other, when you draw many H2O molecules around one another, what do you see? Do you see strong covalent bonds within molecule? Remember this statement here, strong covalent bonds within molecule. So you see covalent bond in this molecule, in this molecule, in this molecule. These molecules as well. But then what do I mean by weak van der Waals force between molecules? We mean in here, you have these weak forces. You have these weak forces between the molecules. This applies to both the elemental simple molecular substance and the compound simple molecular substance. You see? Okay, did you get what I mean? You have the same thing in like each and every of these examples. Okay, so within the molecule, there's always strong covalent bond. No matter which example you look at, they are always strong covalent bonds holding atoms together within a molecule. But between molecules, between this and that, this and this, this and this, or any other example for that matter, there's always weak van der Waals force. Okay, this is a very, very important concept. It goes beyond elements. It's not just the elements, they have this feature, but the compounds, as long as they are simple molecular substances. On the next page, we look at another class of covalent bonded substance. What is the other class? Giant covalent structures. They are also elements and compounds, okay, on the next page. So put this down now. We have giant covalent structures. Just like the simple molecular substances, they can exist as element or compound. Giant covalent structure, they can. Do you see that here? I wrote simple molecular substance, they can be elements or compounds. Well, for giant covalent structure, they can also be elements and compounds. So they may be, elements or compounds. And I want to give you a few examples that you have to memorize, okay, all of them. So starting with elements, okay, we have carbon, the element, okay, so carbon can exist in one of two forms, common form, diamond, okay, we have carbon, graphite. So these are elements, okay. We can also have silicon, okay, so Si, or silicon. For compound, there is only one example that you need to know, is SiO2. But actually for diamond, silicon, and SiO2, they share the same structure. So therefore really here, there are only two structures to remember. One is that of diamond. So I want you to practice drawing this a few times at home. Okay. So draw these like dots connected tetrahedrally. Okay, like that. You don't have to draw like a very, very extensive structure of these, but you have to like understand that this structure goes beyond what you see here. Okay, it's larger than what you see in here. You can only show a very simplified view of diamond. Okay, but it actually continues stretching in all dimensions. Okay, so that's diamond. You need to practice drawing this. Okay, as they will probably ask you to draw in the exam. And you have silicon, and then you have silicon dioxide. So note that I'm drawing the same structure for SiO2, and diamond. And the only difference between these is that in diamond, all these atoms are carbon. And in silicon, all these atoms are silicon, Si. Remember the second letter, I, is in lowercase. They are not both in uppercase. Okay, so Si. Okay, what about SiO2? SiO2 is built on the structure of Si. But on top of the Si atom, you have additional O. So can you add a black dot in between? So that's how you draw it. So you have SiO2. So you draw a black dot on each of those lines, connecting them. So this is why I said if you know how to draw diamond, you also know how to draw Si, and also how you draw SiO2. But be careful when you classify them, okay, into like the element and compound. That's because these three, they belong to what we call the elements. Okay, so they are the element because they contain only one type of atom. But SiO2 is not an element. Okay, it is a compound, as it has both Si and O, meaning there are two or more types of atoms involved. What about graphite? Do you all know how to draw honeycomb? What kind of geometric shape can you observe in honeycomb? Hexagons, yeah. So therefore now, can you draw carbons connected by connected in a hexagonal manner like this? Okay, and just like diamond, it is a very extensive network. Therefore, the term giant covalent, I think this is a very fitting name. Giant means these structures, they are not like as small as what you see in here on the screen. They extend beyond what you see on this diagram here. And graphite is very, very special structure, unlike the other two. That's because it exists as a layered structure, like wafer. So you know wafer, or pancakes. So they stack on top of one another. With graphite, this is a huge, giant covalent structure of one layer of graphite. Below that, you will find another layer. And below that, you will find yet another layer. So many layers of graphite is stacked on top of each other like pieces of paper. So if you look at this as like a single graphite layer, inside pencil, what will you find? You will find layers of graphite on top of one another. And when you write, you are actually shedding layers upon layers of graphite onto the paper. So this is how you write. This is inside the pencil. Well, not this pencil, I mean the real pencil. When you're writing, you are actually shedding layers upon layers of graphite on the paper. So this is how you leave a mark on the paper, okay? And it is black, so graphite is a black substance. So below, we will look at the difference between simple molecular substance. I want you to go back and forth. Look at these structures, simple molecular substances, and then go back and look at the giant covalent structure. What is the main difference that you see? In giant covalent structure, you will see mostly strong covalent bonds. You don't find any weak van der Waals force. Well, at least not for diamond and silicon and SiO2. You will see only strong covalent bonds throughout the entire structure. You don't find any of those weak forces. You see yellow weak forces in here, right? Called the van der Waals force. But do you see any in here? No. Well, except graphite. Graphite is a very, very special case. Can you put a around it? And write down the description below. Note. All giant covalent structures except graphite. So all giant covalent. Sorry, it stopped again. Seems like no matter. Yes, I know. So even if I tap on the screen, it will just speak. So write down this very, very important statement. All giant covalent structures except graphite, okay, have only strong covalent bonds. Okay? So what's so special about graphite then? Is that graphite has, on top of strong covalent bonds, it has some weak van der Waals force. Okay? So, but other than graphite, all other giant covalent structures, they have only strong covalent bonds. Okay, so and I want you to write this down under each of these. Okay, for me. Yeah, so all giant covalent structure except graphite. Okay, so this is graphite. So what makes graphite the exception then? Well, in graphite, you will see also weak van der Waals force. Because graphite is the only structure with a layered structure. The other ones, carbon, silicon, and SiO2, they are all continuous, okay, from the top to bottom. So they are continuous throughout the structure. They are all connected by these strong bonds. Carbon, silicon, and SiO2, they are all continuous structure. Graphite is not a continuous structure. Well, you can argue that it is continuous along this plane, but it is not continuous between layers. You see these layers, they are disconnected, but they interact through these weak forces. Okay, so this is the only structure with a sheets-like layer. The other three, they are not sheets-like layer. They are a single, giant, extensive network. Okay? Right. Can you put down? You have strong covalent bonds within a graphite layer. So within a graphite layer, but then weak van der Waals forces between graphite layers. So weak van der Waals force. So in this regard, it is quite similar to a simple molecular substance, I say. Okay, so weak van der Waals forces between graphite layer. Okay, right, so between layers of graphite. And you may want to annotate on this diagram where one layer of graphite is found. So this is one layer of graphite. This is another layer of graphite. Okay, so you have graphite layer. Okay, so you have, so these are layers of graphite. Okay, so remember this very interesting property. Okay, all giant covalent structures except graphite have only strong covalent bonds. With graphite, it has not just strong covalent bonds, it has also weak van der Waals forces. And then we will look at the unique property of diamond and graphite. So what can you think of, like when I say diamond, what kind of property do you associate diamond with? Is it a very soft or very hard substance? Hard, okay, it is the hardest naturally occurring substance. So on the side, I will write down some interesting note about these structures, okay, and I wanted to put them down. Starting with carbon, diamond. You see I'm writing C bracket diamond because both diamond and graphite, they are two different forms of carbon. Okay, so you may want to write carbon on top first. So carbon. What do you know about carbon? Carbon has atomic number 6. What is its electron arrangement? 2-4. Okay, so electron arrangement is 2-4. That means it should have 4 outermost shell electrons. Okay, so can you highlight this number and then draw out carbon in here, showing 1, 2, 3, 4 electrons. So that means carbon can potentially form 4 bonds. Because it has 4 electrons on the side, it can potentially form 4 bonds. Write this statement here. Because, okay, carbon has 4 outermost shell electrons, it can potentially, not always though, okay, so potentially form 4 bonds, okay, at maximum. But then when you look at graphite and diamond, tell me what you see. In diamond, how many bonds is each carbon forming with its neighbors? When you look at this structure, how many bonds? How many other carbon is each carbon bonded to? 4, right? So you see 4. So you have, you may not need to draw this, okay? You can just refer to the diagram you drew on the left, okay? So you can see that each carbon is connected to 4 other carbons, okay? So what does that mean? It means carbon is using all 4 of its valence electrons or its outermost shell electrons to form bonds with other carbons. So can you put that? In diamond, each carbon, just focus on this carbon if you don't know which carbon to look at, okay? Focus on this carbon. Each carbon forms 4 bonds using 4 of its 4 outermost shell electrons. So 4 of its 4 outermost shell electrons. What about in graphite? Do you remember what the structure is like in graphite? It's like a honeycomb, right? Remember, there is hexagonal layers of carbon. So now can you tell me, I'm not telling you the answer, how many carbons is each carbon in graphite bonded to? Is it 2 or is it something else? Okay, mind you, this structure is just part of the entire structure. You may want to look at things near the center. You don't want to look at things on the side. If you look at things on the side, you will be blinded by the fact that there's another carbon there, right? Yeah. So try to look at things at the center. So what is the answer? 3, right? So we all agree they're 3. Again, if you don't know which carbon to look at the ones near the center. Don't look at the ones around the edges, because those around the edges, they are again connected to other carbon. It's just that you didn't show it. So can you write down, in graphite, each carbon forms 3 bonds. So that means how many electrons is each carbon using only? It's using only 3 of its 4 outermost shell electrons. That means there's a spare one. And what will happen to this spare one? It will become delocalized. Okay, so you can potentially use up all 4 of its electrons. But carbon, because it is forming only 3 bonds, so it is only using 3 of its 4 outermost shell electrons. That means there is one that can be delocalized. Okay, and this explains one unusual property of graphite. Is graphite a metal or is it a non-metal? Graphite is actually a non-metal because it's carbon. Carbon is found on the right-hand side of the periodic table, which makes it a non-metal. But then I say graphite is unusual because it is a very good conductor. You know, non-metal, they are generally insulator, right? But what makes graphite so conductive is the unused electron. It delocalized, okay? It is delocalized. That explains its unusual property. So can you write this additional statement down? Therefore, one electron can be delocalized to form a delocalized sea of electrons. Therefore, we say graphite is an excellent conductor. Okay, if you have delocalized electron, so you can draw an electron aside. This is an electron given up by carbon. This is because there is one unused electron. Okay, in diamond, are there any spare electrons in diamond? Are there any unused electrons in diamond? No, because carbon, like I said, it has used up 4 of its 4 outermost shell electrons. So therefore, you can put down no electron can be delocalized. So what can we say about diamond? Is diamond a conductor or is diamond an insulator? It is an insulator. Okay, so no electron can be delocalized, and therefore we say diamond cannot conduct electricity. So diamond is an insulator. Yeah, but look that they are both examples of carbon. But you see these different forms of carbon, they can have very, very different properties. Okay? Right. And the property of carbon, okay, we can also look at the hardness. Okay, so in terms of hardness, what can we say about these two structures? Okay, first, I want you to write down a description here on the side. What is this description about? This is the description about electrical conductivity. So electrical conductivity. We will now turn our attention to another property difference between the two forms of carbon. It is the hardness difference. So hardness. Okay. So these two different forms of carbon, they can have very different electrical conductivity, and they can have different hardness. So first, I want you to draw diamond again. Yeah. So and hopefully after today's lesson, you know how to draw both of these structures very well. Okay. So can you draw diamond again? Yeah. So you have carbon, 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 carbon everywhere. You see. So all the carbons in these structures, what are they locked in? They are locked in a network of atoms, okay, connected by strong covalent bonds. That means the structure is very, very rigid. Okay, imagine carbons as like spheres connected by these rigid rods, okay, called strong covalent bonds. Because these bonds are very, very strong, it is very difficult to break. Okay, it will mean that the structure has it cannot tolerate any movement. Okay, because the bonds are all very rigid. They're not like made of jello. They are all made of, you know, rigid, okay, bonds. So you cannot move the structure at all because all these bonds are very strong. So this explains the hardness of diamond. So you can say diamond is hard. So write this down. Diamond is hard because all the carbon atoms are bonded by strong covalent bonds. It does not tolerate any degree of movement. Okay, so strong covalent bonds. Just think of this as rigid stick. Okay, so this is analogous to rigid stick. If you have a lot of spheres connected by rigid sticks, okay, you cannot move the structure at all. That's what makes diamond so hard. Okay, so diamond, okay, is the hardest naturally occurring substance. So you may not know that the armor of the tank, tank, okay, they are made of a material similar to diamond, okay, it's silicon carbide, okay, yeah. So but then so this is what makes the tank armor, so tough, okay. So diamond is the hardest naturally occurring substance. And then graphite. Graphite can't be any more different. You can't write with diamond. Okay, yeah, so the price aside, okay, even if you can amass a lot of diamond, you wouldn't be able to write with it. That's because diamond is really hard. Okay, you may be able to cut a piece of paper with a diamond pen, but you cannot leave a mark on the on a piece of paper. But why can you write with graphite? That's because graphite is a very, very soft substance. Okay, so you see they are kind of opposite each other. So that's how we remember it. In terms of electrical conductivity, diamond and graphite, they are like complete opposite. One is a conductor, one is an insulator. In terms of hardness, they are also like complete opposite. Diamond is very hard, and yet graphite is very soft. But this time, we explain its softness with another feature of the structure. So now, I want you all to draw the hexagonal layers again. But the difference this time is that I want you to draw two layers. Okay, in exam you don't have to draw more layers than two. Okay, two I think is more than enough. So just draw two layers here. Remember I compare the structure of diamond to like wafer. Okay, so you have many layers of graphite in here. So graphite has a layered structure. So put this down first. Because graphite has a layered structure, what do these layers interact through? Is it strong covalent bonds or weak van der Waals force? Weak van der Waals force. So that means, is it possible that you displace one layer relative to another? You can, because these forces are very weak. These weak forces in yellow, they are weak van der Waals force. Okay? So this is to be contrasted with the strong covalent bonds. In here, why can't you move this atom relative to another? Why can't you do this? That's because this is a rigid rod. It doesn't tolerate any degree of movement. Hold all in here. Why can you shift one layer relative to the other without much problem? That's because these forces, they are not rigid rods anymore. They are called weak van der Waals force. So this is why you can slide layers next to one another. Is it clear? Okay, so this has to be crystal clear. So graphite has a layered structure, complete the sentence. Okay, which has, and each layer interact with the other layer through weak van der Waals force. Okay, so through weak van der Waals force. This is why I stressed the difference between like covalent bond and van der Waals force. If you don't know which one is stronger, which one is weaker, you wouldn't be able to explain the property. So weak van der Waals forces. So therefore, you can put down, this is what you have before, and this is what you have after. Okay, so after you slide the layers apart, you see it doesn't take you much effort to shift one layer relative to the other. These are easily broken. Okay, so because these forces, right, so these forces can be easily broken, therefore it is possible to slide the layer. Whereas on the left, these forces are very strong. It is impossible to slide the layer on the right. So these forces always do a side-by-side comparison. Okay, when you do revision. If not, you wouldn't see why diamond is hard, graphite is soft. So these forces are very strong on the left. Therefore, not so easily broken. And if they are not easily broken, this is why diamond is hard. It cannot deform. Okay, and cannot deform. And on the right, graphite, because the layers they can be they interact through weak van der Waals force, which can be easily broken. It is possible to slide layers upon layers of graphite past one another. Very clear, right? Okay. So and on top, I want you to add back a summary sentence, and this is that. Diamond and graphite, despite both being forms of carbon, they have different hardness and electrical conductivity. Okay, so you can put this on top here. There's still some space in here. So even though graphite and diamond, they are both carbon, so graphite and diamond are both carbon. They have very different, and then you can put down the blue words, electrical conductivity and hardness, okay, due to the difference in bonding and structure. So very different hardness and electrical conductivity. Any question on this first? Any question? Yeah, let me zoom back here so you can copy the stuff that you haven't copied. So the before and after is to show you what happens when you slide the layers apart. When you slide the layers apart, you can quite easily slide them apart. So what are some uses of diamond and graphite that you can think of? Well, don't tell me jewelry, or of course diamond can be used in jewelry, but you know it's not a practical use, right? It's just used because of its, like attractive appearance. Diamond, because of its hardness, it can be used to tip drills. Okay, you know when you build tunnels through the mountains, okay, you will need to drill your way through the mountain, right? Those drills, they are tipped with synthetic diamond, not the real deal, of course. If it's made of the real deal, I don't think the tunnel would cost that little, okay? So it should be many, many times that. So can you put down some uses of giant covalent structures in relation to their properties? Okay, so giant covalent structures. First, we have diamond. Diamond, because it is very hard, it can be used to tip drills. So used to tip drills. So this is what that means. You have the drill head. On top are many, many tiny pieces of synthetic diamond, okay, distributed on it. So these are synthetic, man-made, okay, diamond. So what is this property? What is this application based on? You can say because diamond is hard, so we can use it to tip drills, okay? And it can be used as an abrasive. So do you all know what abrasive means? No. You have used sandpaper, right? What do you use sandpaper for? For polishing surface, right? This is what an abrasive means. Abrasive would be used to polish surface. So theoretically, you can use diamond as an abrasive. So use as an, even if you're not going to use this term in exam, make sure you understand what that means. Okay, like sandpaper. Okay, so abrasive is something you use to polish surface. That's what abrasive means. And then we have graphite. So graphite has two unusual properties. Let me test if you remember that from moments ago. What are two unusual properties of graphite?
It's electric.
It's an electrical conductor, yes. What about its hardness? It is soft. Can you think of a use of something soft? It's as a lubricant. It can be used as a lubricant. So you know, yeah. Why is that? That's because when you apply, imagine that you have two surfaces here. Okay, you know normally, as you may have learned in physics, okay, what causes friction? Friction is caused by the rough edges, okay, on the surface. So even when you think that, oh, I have two pieces of paper, these two pieces of paper, they look very flat, right? But then microscopically, if you zoom in really, really close, you will see that between these two surfaces, there are many jagged edges between the layers. This is what causes friction, okay? But what is the solution? What if I want to reduce the friction between two layers? Easy. You just take a spray can, spray graphite onto both layers. And do you remember what is the force that hold graphite layer together called? Yes. So you are transforming those jagged edges into two layers that interact only by wind when possible. So you can now slide them apart. So you can do an experiment. You just need a piece of paper and a pencil. So on a piece of paper, you split the piece of paper into two halves. So on the left half, you don't do anything to it, okay? And then you run your finger along it, and it feels rough, right? Well, maybe you can say the paper feels soft. But what if you use a pencil to sketch? Just make one side of the paper black completely, and then run your finger on it again. It should feel smoother than the layer without graphite applied. You can try. You can try. Take out a piece of paper and then use your pencil to do some sketching in here so that one part of this paper will become completely black. Run your finger on that part of the paper that has graphite mark on it, and then move your finger onto the other side without any graphite, and tell me back which one feels smoother. The side with graphite on it should feel smoother. This is to highlight the property of graphite as a lubricant. Okay, the use of graphite as a lubricant. So can you write down two applications? Number one, it is used as electrodes. Okay, so electrodes, they are rods that conduct electricity. So I don't want you to take apart a battery, but let me tell you, inside a battery, you know the AA battery, there is a zinc cap. Okay, so this is a steel cap, sorry, this is a steel cap. And then under the steel cap, you have a rod made of graphite. So don't take apart a battery, just take my word for that, okay? This rod is graphite rod. Why would you see graphite in here? That's because it's a conductor. You know, you wouldn't use something that does not conduct electricity inside a battery, right? Okay, for obvious reason. So this is graphite rod. It is used as an electrode, okay? So graphite electrode. An electrode is something that conducts electricity. So graphite, that is. So write down why this is used in this case. Because it is a conductor. Yeah, what about the second property of graphite? Is that it is used as a solid lubricant. So what's the advantage of using a solid lubricant over a liquid lubricant? So you know sometimes when the door hinge becomes rough, you will spray something called WD-40. Yeah, you may have used that before, right? Onto the hinges, okay? So that is a liquid lubricant. So what's the advantage of a solid lubricant over a liquid lubricant? Is that
it won't get wet. The surface won't get wet.
well, you can look at it the other way. solid lubricant will not dry out because they are already solid. Okay, so they will never dry out. Okay, so this is because, write down which property is it based on. Layers of graphite interact by weak when the Wallace force. And the last use, so at the last use, of graphite is used in pencil, okay? So, right, yeah. So here, write down the third and the last use, okay? So weak when the Wallace force. So the last use is used in pencil. Yeah, and why is that? That's because when you write and you leave a mark on the paper, what is actually happening is that layers upon layers of graphite, they are being shattered, okay, onto the piece of paper. So I'm showing you what happens on the pencil. So this is what you will find on the pencil. There are multiple layers of graphite. And when you write, you are depositing, you're leaving behind layers upon layers of graphite. So this is what you see at the pen tip of the graphite, or the pencil. Pencil or graphite, it consists of a sheet-like layer, many layers. And when you write, you are sharing, okay, layers upon layers of graphite on the paper. Okay, and this is made possible because the interaction between graphite layer, is it strong or weak? Weak. It is because the interaction between the layers that are weak that it is possible to shed layers. I mean, if it is hard, like diamond, okay, if you can break the hard bonds, well then technically you can write with diamond, but we cannot. This is because these bridge bonds, they just don't break. They just won't break. So write down, it is used in pencil, again, because the layers of graphite, they interact through weak when osmosis. Same application here. Okay, same property and same application. So any question so far? No. Okay. Then we look at the general properties of ionic compound, metals, and covalent structures. Okay, so we look at here, put down properties of ionic compounds. Okay, and then we will look at properties of covalent compounds side by side. So, let's call it ionic structure. Okay, so ionic structures. And then on the opposite side of the page, I want you to put down properties of covalent structure. Okay, so write them on opposite side of the page. So starting with properties of ionic structure, okay, we'll look at the melting and boiling point. So they tend to have high melting and boiling points. Whereas for covalent structures, so note that for covalent structures, there are two subtypes. Okay, they are like giant covalent structure and simple molecular substances. Okay, so under giant covalent structure, I want you to put down these subclasses first. So there are simple molecular substances and giant covalent structure. So depending on which group you are looking at, they may have different properties. Okay, so we will compare them side by side now. Okay, so under covalent structures, there are two subtypes. So for simple molecular substances, they have low melting and boiling point. But for giant covalent structure, they, like ionic structure, they have high melting and boiling point. Okay, why is that? Can you think of an example of each type of structure here? What is an example of ionic structure? What is table salt?
NaCl.
NaCl. So can you put NaCl here? What is an example of simple molecular substance? What is that gas that we breathe out, or the gas that we breathe in?
Oxygen.
Oxygen is what we breathe in. CO2 is what we breathe out. They are both examples of simple molecular substances, okay, as they contain discrete molecules with a countable number of atoms, okay. Giant covalent structures, they contain an uncountable number of atoms, like diamond, like graphite, like silicon. So now we are going to explain and compare the physical properties. Why do ionic structures have high melting and boiling point? That's because what is the bond found in ionic structure called? Is it ionic or covalent? Yeah, apparently. In ionic structure, you find ionic bond. This is why we call them ionic structures, right? So you have positive and negatively charged ions that interact through strong covalent bonds, okay? So you can put these strong bonds in here. Every time I draw a straight line, okay, not dotted line, that represents strong bonds, okay? So you can say because ions are held by strong covalent bonds, which are difficult, strong ionic bonds, I mean. So strong ionic bonds, which are difficult to break. Therefore, they have high melting and boiling point, okay? So, which are difficult to break. Therefore, requires a lot of heat to melt or boil. Like I say, a lot of students miss this statement in the answer, okay, which is why you won't score fully. You have to say, well, if they are so difficult to break, so what? So that will mean it requires a lot of heat to melt or boil these structures. Okay? Right, you must not forget this last sentence here, okay? Therefore, the high melting point. What about simple molecular substance? Okay, let me also add water in here. Can you tell me when you boil water, what does water become? Does water become H and O atoms, or does water become steam? Steam. What does it show? It shows that when you boil something with a simple molecular structure, are you breaking the strong covalent bonds, or are you just breaking the intermolecular forces?
Breaking the
Intermolecular force. Okay, just think about what we just said. If when you boil water, you are breaking the strong covalent bonds, then what will you get after you boil water? You will get individual hydrogen atom and oxygen atom. And you know for a fact that did not happen, right? So that means when you're boiling, when melting or boiling, so melt, when you melt or boil a simple molecular substance, you are only taking apart the weak van der Waals force. The strong covalent bonds, they remain intact. They are never broken. Okay, so you must know this. Okay, so only the weak van der Waals force needs to be broken. The strong covalent bonds will not change at all. It will not be broken, or nothing will happen to it. So only weak van der Waals force will be broken. Underline the word only. The strong covalent bonds need not be broken. So if you don't need to break strong bonds, then does it take a lot of heat or very little heat to melt or boil them?
Very little.
Very little. Okay, so everything makes sense now. Okay, now that you know something about the bonding. So can you write down a similar statement to the one we just wrote? Okay, so you can write down, so in here, because, so in here, write down, because molecules, okay, so molecules, so these are molecules, and here these are ions. We have cations and anions. Okay, so know what we are referring to when we write these, okay? So molecules, they are attracted to each other by weak van der Waals forces. So by weak van der Waals forces, it means it doesn't take much heat to separate these forces, okay? So therefore, you can say that which are quite weak. Therefore, little heat is needed to melt or boil them, resulting in them having low melting and boiling point. Okay? Think about it. Oxygen. In what state does it exist? Oxygen. Oxygen is a gas. Okay, carbon dioxide is a gas. A lot of these simple molecular substances, in case you haven't noticed already, they are mostly liquids or gas. Very rarely do you see a solid, but I have to emphasize that it does occur. Okay, solids do occur, like iodine. So which are weak. Therefore, requires only very little heat. So very little heat to melt or boil, resulting in them having low melting boiling point. Okay? What about diamond? Is diamond something easy to melt?
No.
No. In fact, diamond has close to 4,000 degree a melting point. Why is that? That's because when you look at diamond, yeah, let me just draw this again. Yeah, hopefully by now you know how to draw diamond. Okay, yeah, so what interaction holds the carbon atoms in position? Those are called, yeah, strong covalent bonds. Okay, so you can extend this network like that. Well, yeah, and then you get this structure in here. So in diamond, only strong covalent bonds are present. So now we write the subject here is atoms. So atoms are bonded by strong covalent bonds. And because these are strong, they are not so easily broken. This explains why, just like with ionic bonded structure, yeah, I'm lazy, I'll just copy this, but you cannot be lazy, you have to write it, okay? So write down which are difficult to break. So strong covalent bonds, which are difficult to break. So it requires a lot of heat to melt or boil them, resulting in them having high melting point. So you see the property, we can relate it to the structure. There is a reason for these structures having these properties. Okay? So the second property that I want to discuss with all of you is, okay, maybe you can finish writing this down first. So atoms, right. Note the difference in the subject here. Okay, so you have ions, whenever you talk about ionic compound. You have molecules, whenever you talk about simple molecular substance. And you talk about atoms, when you refer to giant covalent structure. Okay, so you have, yeah, these two. Now the second property is the electrical conductivity. Okay, so do ionic compounds conduct or do they not conduct electricity? From our discussion last lesson, not this lesson. Your answer should be, it depends. Yeah, in which states, okay, will an ionic compound conduct electricity? Referring back to what we discussed last lesson. Liquid, meaning molten liquid, or aqueous, but not in solid. Yeah, why? Because in solid, can the ions move around?
No.
No, why can't they move around? Because of the strong ionic bonds. The ionic bonds hold them in position, like chains, right? Think of them as like some chain. They all chain up together. So this guy cannot move very far away from this ion because of the strong ionic bonds between all these ions. But then we say there are two things that you can do to break the chains. What is it? Number one is by melting or heating. So we say heating can break those chains. Okay, the chains called ionic bonds, and then you get mobile ions. Okay, so you see a bunch of criminals running loose. Okay, and then here water can also split or break the ionic bonds. Again, you will then have mobile ions. So therefore, let's go back here and fill out what we just said. The second property here is it is an insulator in solid state. But
Wait.
yes.
Why can water break the strong ion?
Why can water? That's a very difficult question to answer. But remember, I said H2O is actually a schizophrenic molecule. It has some positively charged end and some negatively charged end.
Yeah.
So when you put a bunch of positive and negative charged ions in water, let's say this is an ionic compound, which is a solid. How can water break up the ionic bond? It's by surrounding the ions, okay, like this. So let me just put it here. Can you tell me which end of water will move near the positive ion?
Oxygen.
The oxygen, yes. So therefore you will have something that looks like this. Let me draw this. So you have this, and then you have this, and then you have this. You don't have to draw this in the exam, but because you asked, okay, so I will just put this like this. And then you have H2O, and then finally you have H2O. So to answer your question, how can ions be split by water? Okay, how can the ionic bonds be broken by water? It's because the water, it will just insert itself between the two ions. Okay, and then it will say, okay, you should not bond with him anymore. You should bond with me. Okay, yeah, so it's kind of like it's trying to force apart these friends. Okay, so they are all friends to one another. But then oxygen say, okay, I don't want you to make friends with him anymore. Make friends with me. Okay, so oxygen inserts itself between the positive and negative charge and separate. Okay, but you don't have to know the detailed explanation. But yeah, this is how it works. Okay, so can you put down just a very, very short description? Water has two charges on the same molecule. Okay, on the same molecule. H is positive. You will know why in Form 5. Okay, so H is positive. O is negative. Then what happens? Then H2O. So you see this is an H2O molecule coming in. It will insert itself here. It says, okay, you should stop making friends with this guy. Okay, make friends with me. Okay, I'm O. I'm also negatively charged. This is how it works. Okay, so just put down then H2O can insert itself, okay, between the positive and negatively charged ions. So positive and negative charged ions. And then what? Then it will form attraction with the ions instead. Okay, so effectively breaking the ionic bond. Okay, so these are attractions. Okay, so these are attractions. Originally, these are the attractions, but now you're breaking these attractions. You instead replace them with the yellow attraction. Okay, right. So finally, the original attraction between the positive and negative ion, these are called strong ionic bonds. They become replaced. Okay, yeah. So it's replaced with these. Okay, so you have positive ion, negative ion, you have then the water. Okay, so these are the H2O, 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 and then you have H2O, 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 H2O. Okay, so that's how it works. Yeah, so it is an insulator in solid state, but a conductor in what state? In two states, in molten and aqueous. Yeah, so, and if you don't feel like writing such a long word, just write bracket S for solid, bracket L for molten, bracket AQ for aqueous. Okay? Yeah, let me finish this. Because, okay, in solid state, there were no mobile ions. Okay, so there were no mobile ions. But when you melt or dissolve the ionic compound in water, you will get to a state with mobile ions. Yeah, so use the word mobile ions in the exam. Okay, so you have mobile ions. From not having mobile ions in a solid state to you having mobile ions in molten or aqueous states, this is what makes them conductive. Okay, so write down no mobile ions in solid state, but have mobile ions in molten and aqueous. Okay, and I wanted to finish these two worksheets. Okay, I have not provided you with the answer, so you have to bring this back. And right, and guys, I will be leaving in November. Okay, in November 15th. Okay, so and in this time, yeah, you can like ask me questions. Okay, because I can't handle Form 1. I really cannot handle it. Like it's like a disaster when I walk into the classroom. Okay, it's like I walk into a market. Yeah, okay. Yeah, when I talk, yeah, I've only got one voice, but they've got 30 30 different voices, so like I can't even hear myself when I talk. Okay, so yeah, 50, 50. Yeah, just telling you. Okay, yeah, just telling you it's not because of you. Okay, you have to enjoy it. Okay, just yeah. I will upload